Okay, thank you very much for the invitation to speak. It's great to be back in China. My talk today is titled The Large D Black Hole Membrane, and is about a simplification of the dynamics of black holes that happens in a large number of dimensions. Okay, the talk is based on three papers I've been involved in recently, along with ongoing work, some by myself and some by other people. It builds crucially on observations and earlier work by Emperan, Suzuki and Tanabe, and ongoing contemporary work by Tanabe, Suzuki, Tanabe and Emperan, Suzuki, Tanabe and collaborate. Okay, so let's start. Classically, suppose we're doing classical gravity. Okay, classically, if you're outside the black hole, everything inside the black hole is causally disconnected from you. Okay, so you might think that, okay, so because of that, you could sort of just ignore the interior of the black hole. You could just ignore the interior of the black hole if your purpose was to try to predict the things you could observe sitting outside the black hole, and just let your space-time end at the future event horizon. Okay, now the condition of smoothness of this event horizon can be worded as a boundary condition on this event horizon. This boundary condition can be worded in suggestive language with appropriate definitions. After making appropriate definitions, the boundary conditions can be worded in terms of, can be worded as relations between in the induced metric and gauge field on this event horizon, and canonical momenta to the induced metric and gauge field on the event horizon. And can be worded in terms that take sort of a familiar form in material terms. For instance, a boundary condition that reminds you of Ohm's law on this event horizon membrane. Everything I've been describing here is old wisdom that goes by the name of the membrane paradigm of black hole physics. Okay? So, just to summarize, the membrane paradigm is the idea that you can just throw away the space-time inside the event horizon and deal with a sort of membrane on the event horizon, smoothness of the membrane on the event horizon. Smoothness of the event horizon gives you boundary conditions at the event horizon. That's very nice and in some ways very elegant. But unfortunately, Einstein's equations are as hard to solve just outside the event horizon as they are, a little inside the event horizon. And so this membrane paradigm, while very elegant, doesn't buy you much, practically speaking, if your goal is to find an efficient way of solving Einstein's equations. Okay? In this talk, I'm going to describe a sort of primed up membrane paradigm, something that does better. I'm going to describe a membrane in which captures all of the physics, not just off the horizon and the inside of the black hole. Some membrane that captures not just, some effectively what's going on inside the black hole, but the physics of the whole of the space-time that makes up the black hole. Okay? Now, that I can do this, as often is the case in physics, that I can simplify things in this manner, as often is the case in physics, requires a parameter. And the parameter that I will use that will allow me to do the simplification is large d, where d is the number of dimensions of space-time. Okay, so let's move. To start the contentful part of the talk, let me remind you of the metric of a black hole in a large number of dimensions. Okay, what I've written here is the metric of a Schwarzschild black hole in a slightly unfamiliar coordinate system. This unfamiliar coordinate system is called the Kerr-Shield coordinate system, and I've written it in this coordinate system because it will prove useful for me later on. Okay, so in this coordinate system, the black hole metric takes the form metric of flat space plus some corrections. Notice in particular that the corrections go to 0 at infinity, so the space is flat at infinity. Okay, the metric here describes a black hole moving at some constant velocity. That constant velocity is u mu. U mu is a velocity vector, so it squares to -1. And the r coordinate is just the magnitude of spatial distance is orthogonal to the velocity. So if u was time dt, r would be radial coordinate in radial distance in polar coordinates. Okay. Now, just looking at this metric, or a Schwarzschild coordinate version of this metric, Emperor, Suzuki and Tanabe made the following observations. They observed that if you are sitting at any r larger than r naught, you hold r fixed and take the limit d goes to infinity, then this term goes to 0, and so this metric reduces to flat space. So we conclude from this that if you stay at any point outside the black hole, hold where you are fixed, take d to infinity, you just don't see the black hole at all. On the other hand, if you do something a little more clever, that is, you take r to be r naught into 1 plus capital R divided by d minus 3, hold capital R fixed, and then take d to infinity, then you can easily check that this quantity doesn't go to 0, but just becomes e to the power minus capital R. So in this limit, the metric of the black hole is flat space plus a tail. This tail goes to 0 as capital R goes to infinity. And so we see that the black hole develops a sort of thickness, a thickness whose size is r naught divided by d. Okay? So there are two length scales in describing this black hole physics at large d: the size of the black hole and the thickness of the black hole. The thickness is smaller than the size by 1 over d. Okay? This was key observation made by Emperor, Suzuki and Tanabe. Okay. Now, that's great. I'm going to consider something a little more general. I'm going to consider a metric that looks very similar to what I had in the previous transparency. There's flat space plus some stuff. In the previous transparency, this stuff was drm minus um by something particular. Here I take a generalized version of that metric. I look at the metric. I look at the metric gmn is eta mn plus n minus um by rho to the power d minus 3. Okay, so now what are all these quantities? Rho here is any function that varies on length scale 1 rather than, let's say, 1 over d. Okay, any smooth function of spacetime. N is the normal vector unit normalized, so just d rho unit normalized. With this normalization done regarding rho as a function that lives in flat space. So the metric that goes into this normalization here is the metric eta. U squared is any one-form velocity field that lives in flat space. It's also normalized to be minus 1 in the metric eta. And u dot n are taken to be 0. Okay? So the data for the construction of this metric is a smooth function, a smooth one-form field satisfying some elementary algebraic constraints. Okay, now this is just some metric I've pulled out of a hat. What can I say about it? Well, the first thing you can say about it is that everything I said on the previous transparency holds for this metric in slightly modified form. In particular, if you are at a distance rho minus 1, which is much, much larger than 1 by d, if you're at a point where rho minus 1 is much, much larger than 1 by d, then this term very rapidly vanishes and the metric reduces to flat space. Okay, so this describes a metric that becomes flat once you go more than a distance 1 by d away from the surface, the distinguished surface rho equals 1. Now there's something else that's sort of nice about this metric, and that's this. This n vector field, which was the normal to rho, to surfaces of constant rho, was chosen to be normalized to 1 in the metric eta. But if you compute what the normalization of this n vector field is in the metric gmn, it's an easy calculation to do. To check that with this metric, you get 1 minus 1 by rho to the power d minus 3. This, in particular, tells you that the submanifold rho equals 1 is a null submanifold. And though we have to do some acausal reasoning to establish this, the dissipative nature of the membrane equations I will soon be finding strongly suggests, if not proves, that this null manifold is not just any old null manifold, but a very special null manifold for the space-time, namely the event horizon. Okay? So, we've seen two things. We've got a we've got this null manifold rho equals 1, and space-time a little bit away from this null manifold very quickly reduces to flat space. Okay, so now I'm going to proceed adopting some of the philosophy of this thing called the membrane paradigm. I'm going to be uninterested in the interior of the event horizon of the black hole because I'm only interested in predicting what I as an external observer can see. Okay, we've also seen that, so we are uninterested in the regions where rho is less than 1. We've also seen that we don't need to bother about regions where rho is much, much larger than 1 by d, because in those regions space-time is flat. Okay? So everything interesting in these metrics happens on a length scale of thickness 1 by d around the surface rho equals 1. Okay? So now, so far I've just written down metrics for you. I now want to try to promote these metrics to solutions of Einstein's equations. So this is how I proceed. The first thing I do is the following. I ask myself, suppose I have, suppose I have a metric of this form and I evaluate Einstein's equations on it in this membrane region. This region within a distance 1 by d of the surface rho equals 1, I'm going to call the membrane region. So suppose I evaluate Einstein's equations on this metric in the membrane region. What should I expect terms in this equation to evaluate to in powers of d? Well, clearly, Einstein's equations are 2 derivatives in d, and this metric we've already seen varies on length scale 1 by d in the rho direction. So take 2 derivatives of that object, you can get something up to order d squared. So you might expect that this metric, that when you evaluate Einstein's equations on this metric, when you evaluate Einstein's equations on this metric, you will find that the curvature Rmn is of order d squared. That will generically be true. However, we know something else. We know that there is a particular example of these u and rho functions, the example I started my talk with, the example that gave you the Schwarzschild black hole, on which Rmn wasn't order d squared, was just 0. So one can use this fact to demonstrate that if the u function and the rho function are not completely arbitrary, but are chosen to obey a couple of equations. Okay? The first equation is that del dot u is equal to 0. And the second equation is that del square of 1 over rho to the power d minus 3 is equal to 0. These 2 equations were true of the exact black hole solution. And the point about these equations is that it's the only thing needed, the only quantities that appear when you actually evaluate Einstein's equations on the exact black hole solution that contributed order d squared, apart from the obvious d dependencies because of the d power and 1 over rho to the power d minus 3. So if you make this assumption about these functions, okay, then it turns out that Rmn, instead of being of order d squared, turns out to be of order d. This you can just check by explicit calculation, and you can give intuitive arguments that this had to be the case. This is very interesting because it tells you that with these conditions imposed on our metric, the metric solves Einstein's equations at large d better than a generic configuration would, and so suggests that these functions u and the shape of the membrane are collective coordinates for an effective construction of solutions of Einstein's equations in a power series expansion 1 over d. Let's see how this works. Suppose I take now a corrected metric, a metric that is corrected in the form, it had the ansatz metric I wrote down for you in the previous transparency, plus a correction, which is 1 over d times something. I put a counting parameter epsilon just to make a point. Epsilon will be set to 1 at the end of after the point is 1. Okay? So suppose I take my metric, the metric I had on the previous transparency, this metric here, plus a small correction. I'm going to ask, can I find this small correction to ensure that that Rmn, which was originally order d, is now not order d but instead order 1. So Einstein's equations are solved to 1 higher order than they were previously. Okay? This is easy to do actually. You see, just take a look at the powers. We know that when you evaluate Rmn on G0, we get something that's order d. When we evaluate the term that is linear in this G1, we get an explicit factor of 1 by d, and then we get something that's order d squared because there are two derivatives of a spacetime that varies on length scale 1 over d and other reasons. Okay, so the 1 over d cancels the d squared and you get something order d. So these two terms are both order d. And then you can try to choose G1 Mn so that this term cancels that term and you've got a real solution of the equations. Okay? Fine, so let me tell you in 1 minute in a little more detail how this is done. It turns out to be convenient when you're solving this problem to foliate space-time in slices of constant rho. Rho equals 1 is special, but we will foliate our space-time in slices of constant rho. And then we will, and then after this, performing this foliation, we will break up Einstein's equations into dynamical equations that allow us to evolve forwards in rho, and constraint equations. Oh. Oops. Okay, so yeah. Thanks. Okay, so now, as is often the case, the dynamical equations can be used to actually solve for G1 in terms of your G0. I'm running out of time. I've given details of how this is done. It doesn't matter. This G1 dynamical equations give you second order and in the end effectively linear ordinary differential equations in a single variable rho. Okay? Turns out these linear ordinary differential equations are easy enough that you can solve them. And so the dynamical equations just allow you to solve for G1 in terms of G0. And when you impose all the conditions that you must, I must mention some of these conditions. The key condition is that we impose the condition that the correction metric, like your seed solution, decays as rho minus 1 is much, much larger than d, 1 over d, and also that it preserves the regularity of the event horizon. When you do all these, you get a unique solution for G1 from the dynamical equations. Okay, what remains now are the constraint equations. Now there's a beautiful property of Einstein's equations that if you've got your dynamical equations solved everywhere, then you only need your constraint equations to be solved in one slice, because that implies that they solved everywhere. So we can pick our slice. It's convenient to pick the obviously special slice in the problem, namely the event horizon. Imposing the dynamical, now we've got no further freedom. We've completely solved for G1 from the dynamical equations. The constraint equations gives us constraint on the starting point of the solution of this whole process. And it turns out to give you these equations. It recovers the equation del dot u is equal to 0 that we started with, and then gives you another equation of motion that constrains the shape of the membrane and the velocity field of the membrane. Now there's something very important here. The important thing is counting. You see, our ansatz was parametrized by d minus 1 functions. One of these functions was the shape of the membrane. The d minus 2 functions were a velocity field on the membrane. Okay. However, the number of equations we have is also d minus 1 if you just count up these equations that I've written for you. Okay, so the key point is that Einstein's constraint equations give you as many equations as variables for the collective coordinate data that went into parametrizing our class of solutions, and so define a good initial value problem, or at least plausibly define a good initial value problem for this membrane. So in other words, we've now established a duality between two different problems. First problem is solving Einstein's equations for black holes. The second problem is solving the membrane equations for this membrane. You do one, you've done the other. Of course, to leading order and 1 by d. Now we've taken this forward to the next order. At the next order, you get corrections to the old equations. Del dot u, instead of being 0, is something. Actually, it's important to note that something is the shear squared divided by 2 kappa. We'll come back to that. And the other equation of motion gets corrected. We don't have the time to look at it too much. Okay. Perhaps one thing I did want you to look at was this. that if you look at these equations, these are very reminiscent of the equations of hydrodynamics. This here is like an inertial term. This here is like a viscous term. This is sort of like a pressure term. We'll come back to that. Okay, everything I've said can be generalized to the study of a charged fluid. You do the whole construction not with Schwarzschild solutions, but Reisner-Nordstrom solutions. You've got a new degree of freedom, namely the charge on the membrane, and you get a new equation. And the new equation is governs the dissipation of the diffusion of charge. Notice again that there are many very familiar terms to anyone familiar with hydrodynamics. Okay, now that we've got these equations, we're going to start using them. The simplest solution of these equations is a spherical membrane, which is dual to a Schwarzschild black hole or a charged Reisner-Nordstrom black hole. Now, one of the things we did is linearize our equations around this black hole, and we found a bunch of what you might call quasi-normal modes. The spectrum of frequencies of linearization of the solutions around this spherical solution. One of the important things about this is that the spectrum, there were some zero modes, but every time there was a zero mode, it was for a physical reason. For instance, you could set the black hole moving. That gives rise to zero mode. You could set it rotating. That gives rise to zero mode. But all the zero modes you could identify with exact solutions. Apart from that, all the solutions, all the modes of this linearization had a positive imaginary part and corresponding to decay. So, at least at the linearized level, our membrane equations define a nice stable initial value problem. Okay. Moreover, these frequencies can be checked against a calculation done directly in gravity to compute the frequencies of quasi-normal modes around black holes in large D directly in gravity. Turns out this calculation was done by Empran, Suzuki, and Tanabe. Turns out they found that you get a bunch of light modes and then other heavy modes. I don't have the time to describe the details. Our frequencies agree bang on with the light modes, but don't see the heavy modes. We don't see the heavy modes because the heavy modes at frequencies order 1 over d and are outside our approximation schemes. Okay, so you can think of our membrane equations as the nonlinear equations that we've obtained by integrating out the light modes. Integrating out the heavy modes. Nonlinear equation for the light modes by integrating out the heavy modes. Very much like fluid gravity, actually, where you can think of fluid dynamics as the nonlinear equations for the light quasi-normal modes obtained by integrating out the heavy quasi-normal modes. Okay. Now, we'd like, this is nice, we'd like to do more. Suppose the membrane is undergoing some sort of complicated motion, dual to some complicated motion of the black hole. Surely, this thing is going to result in some radiation outside at infinity. And I'm going to ask the question, how do I identify this radiation? Well, at first you might think all you have to do is to take your membrane space-time. All you have to do is to take the membrane space-time that I produced for you and just look at it at very large rho. That gives you a radiation field. But if you carefully examine our approximations for construction of this membrane space-time was good in the neighborhood, in this membrane region. But it required rho minus 1 to be much, much less than 1. So we can't continue the solution to large R. But we can do something else. As we've seen, the solution decays almost to flat space when rho minus 1 is much, much larger than 1 by d. Our approximations for the metric we constructed were good when rho minus 1 was much, much less than 1. So there's this overlap regime in which both approximations are good. Okay? So we can work in this overlap regime, identify an effective linearized solution of gravity, and then continue that linearized solution to infinity to identify the radiation field. There's a very elegant way of doing that second thing. The elegant way of doing that second thing, which works for any reasonable linearized solution of gravity at large d, goes as follows. You take that linearized solution, evaluate the Brown-York stress tensor from that solution on the membrane, and add to that Brown-York stress tensor a contribution that you get by varying a counter-term action, which takes this form. This counter-term action has to be evaluated order by order and 1 by d. I've just written the first two terms for you. That gives you a stress tensor on the membrane, and the role in life of the stress tensor is that it correctly produces the linearized field. It's the stress tensor that, when integrated against a retarded Green's function, produces your linearized field. Okay, so the clean way of continuing the solution to infinity is not to do the continuation directly, to identify a stress tensor on the membrane, and then couple that couple the stress tensor to external gravitons as usual by convoluting against the Green's function. Okay? This is a stress tensor that lives intrinsically on the world volume of the membrane, but it can be promoted to a space-time stress tensor by this construction. And the fact that the intrinsic membrane, our construction guarantees that the intrinsic membrane stress tensor is conserved as a world volume field. It turns out it also guarantees that Tmn Kmn is equal to 0, where Kmn is the extrinsic curvature of the membrane viewed as submanifold of flat space. Okay, and these two conditions turn out to guarantee that this space-time stress tensor is also conserved. Okay, this is the explicit form of the stress tensor for an uncharged, for simplicity, to first non-trivial order, zeroth and first order, in terms of velocity and shape fields. Notice that this first term here describes the motion of dust of density kappa. The kappa is the trace of the extrinsic curvature of the membrane. The second term describes a shear term, and we'll see this later on if I get to later on, that eta by s described by the shear term is will turn out to be 1 over 4 pi. And then there are other terms. Moving on to charge fields, we also find a charge current, but I don't have the time to tell you about that. Okay, now I've told you that our abstract construction ensures that the stress tensor is always conserved. But it's useful to see in the case of the membrane spacetime how that works. So you can just directly compute del mu t mu nu. And if you take that del mu t mu nu and project it onto u, you find that that's proportional to del dot u. So that vanishing is the first membrane equation of motion. And then you take del mu t mu nu and project it orthogonal to mu, and you find that that vanishing is proportional to the other membrane equation of motion. Okay, similar story for the charge current. Okay, great. I'll take maybe 2 minutes, Elias. Okay. Fine. So we've got these nice stress tensors and charge currents. They satisfy two roles. They source radiation. Also, their conservation gives us the equations of motion. It's an elegant way of restating the equations of motion of the membrane. Now, notice that the stress tensor and the charge current are not small. In fact, they're order d. So you might think then that radiation that they emit will be quite substantial. But that turns out not to be the case. And this has to do with an interesting property of Green's functions in a large number of dimensions. The equation del square phi is equal to 0, I'm ignoring the source term for a moment, can be, by change of variables, transformed into a Schrodinger type equation, where the Schrodinger equation is an equation for a mode propagating in a potential which is essentially d squared by 4r squared. So it's a huge potential. Radiation happens when something at r0 tunnels through this, and at energy omega, tunnels through this huge potential, going all the way until it comes out of the potential and then propagates. That's radiation. But this tunneling process causes it to decay very significantly. It only comes out at r is equal to d by 2 omega. And so for that reason, by the time it's come out, the radiation has emerged. You've got only, its amplitude is just 1 over d to the power d. Okay? So another way of saying this actually is quite reminiscent of Mulder-Sener's argument for ADS-CFT. Okay, similar kind of decouplings happening between the two kinds of light modes, the light quasi-normal modes and radiation. The thing that controls this decoupling is large d, and radiation, which is order 1 over d to the power d, is the failure of decoupling. Okay, one can use the area form on the event horizon to deduce an entropy current on this membrane, which from Hawking's area increase theorem can be shown to be always positive divergence, very much like Hong had in his talk. To leading order, this area current turns out to be um by 4, very simple entropy current. Okay, using this entropy current you can find stationary solutions. I don't have the time. There's a long and interesting story. Okay, conclusions. What have we done? We've demonstrated that the near horizon geometry of charged and uncharged black holes decouples from asymptotic infinity at large d. At the classical level, the decoupled theory is governed by a set of equations that describe the propagation of a membrane in flat space. The degrees of freedom of this membrane are its shape and a velocity and a charge density. The membrane carries a conserved stress tensor and a charge current, whose explicit form we've determined to the first couple of orders in large D expansion. There's no barrier to taking this expansion to d to the power 26 if you're good at mathematics. Membrane equations of motion are simply the statement of conservation of these currents and appear to define a well-posed non-gravitational initial value problem. Radiation reflects the failure of decoupling and occurs at order 1 by d to the power d. The explicit form of the radiation fields is obtained by by coupling the membrane, stress tensor, and charge current to linearize exterior metric and gauge fields in the usual manner. Okay, and then there's lots of things that one could try to do, some of which are being done and some of which are more ambitious. Thank you.
Okay, so I'm not really terribly sure about the effects, but is it that particles move with something very long way that process, right? Presumably everything that happens at large D in a black hole kind of space happens in this 1 by d Tensor. Presumably. And I assume that there everything would happen as usual. I don't know. I would imagine that it's a yes, but I know it.
I can just shout. Did you look at what happens if the black hole's extreme, either from charge or spin?
If the black hole, sorry?
If it's extreme.
If it's extreme, yes. So, if the black holes are literally extreme,
Yes.
then our approximation is all right. It's very similar to fluid. You see, in the process of solving these equations, at some point you have to fix an integration constant by ensuring that you don't develop a singularity of product. The danger of developing that singularity was that you had 1 over signal 0, and you could fix an integration constant to kill that. But when the signal 0 becomes a double 0, you need to fix 2 things and you have only 1 thing in your hand. So, very similar things happen in fluid gravity. So I think there's a physical basis. And extremality, the size of this near horizon region becomes infinite. And in some sense, what we're doing is keeping sort of the 0 modes in this near horizon region. It becomes very long, we want to keep all these excitation modes as well, because they also have light.
Sorry, what do you mean it becomes infinite? It grows like D? Or
No, I just mean it becomes infinite because extremal horizons have infinite distance away from any point. ADS, right? Becomes ADS 2. Okay.
Any other questions? In that case, as a